Okay, here we go. First PowerPoint of Bio 202. This is probably the most important PowerPoint of the entire semester because it's material that we're going to use all semester long. That's why you have a homework assignment on this PowerPoint, and you're going to have a 20-point quiz on it. All the other quizzes this semester will be 10 points. This quiz is going to be 20. The stuff we cover in this PowerPoint, you have to know all semester long. So here you see a question from an exam. What is the strongest force on Earth? Student wrote love, and the instructor just harshly crossed it out. I would have given partial credit for that. I mean, if an answer makes me, I think that's hilarious. If an answer makes me laugh, even if it's wrong, I give partial credit. But you can see this is a geology exam or quiz. So what do you suppose the right answer is? What was the instructor looking for? What is the strongest force on Earth from the perspective of a geologist? That would be water. Water is incredibly powerful. Here you see my feet at the Grand Canyon. That's a 3,000-foot drop to the river, to the Colorado River, and that's water that did that. I mean, it took it a long time, but water will cut through anything given time. Doesn't matter, rock, metal, diamonds, you name it. Water will cut through anything, all right? It is the most powerful force. And water is incredibly important in the human body. So let's start taking a look. Fluids and solutes. So fluids, water, and water-like fluids, and solutes are things that are dissolved in the fluid, all right? So your body is filled with many kinds of fluid. That includes blood, lymph. We'll learn about that. You have lymphatic vessels and lymph. Intracellular fluid, that's fluid inside of your cells. Extracellular fluid, fluid outside of your cells. Interstitial fluid, that's fluid in the spaces in between cells. Cerebrospinal fluid, and lots more as well. Fluid is full of solutes. What's a solute? A solute is something that is dissolved in the fluid. So dissolved means they're not visible. You can't see them. They are completely soluble. They are no longer visible. They are completely encompassed in that fluid. Solutes include things like ions, proteins, amino acids, glucose, hormones, gases, and lots of other things as well. To keep in homeostatic balance, remember homeostasis, the most important topic in all of Bio 201 and 202, in all of anatomy and physiology, it's always about homeostasis. You have to move solutes and fluids around. That's what's happening inside of your body at this very moment. So moves are from one compartment to another. For example, from inside your cells, the ICF, to outside the cells, ISF. The fluid immediately outside of the cells would be ISF, which is a type of ECF. I'll keep reminding you about these things. And vice versa, into and out of the blood, into and out of the lymph, and so on, okay? Now, where do you think most of your body fluid is? I mean, all of your body fluid is either extracellular fluid, which is outside of the cells, or intracellular fluid, inside of the cells. Which do you think? A lot of people are surprised by this. Most of your body fluid is ICF. It's inside of your cells. And by the way, that picture is Lower Calf Creek Falls. I spend a month every summer camping by myself in northern Arizona and southern Utah. And I hike to that. It's like a 3-mile hike to the falls. It's great because it's always hot when I'm there. Just tear off all your clothes, run out, dive in, swim right up underneath the waterfall. There's a picture of me. Okay, fluids in the human body. Typical 150-pound or 70-kilogram adult is about 50 to 60% fluid by weight, all right? So you are roughly, just off the top of your head, think of half. Half of you is water. If you weigh 200 pounds, about 100 pounds of that is water, okay? Now, a typical 150-pound person, that would be 40 liters, or 10 gallons. Always, we need to be able to be comfortable, especially with liters, because science and medicine, we don't use things like ounces and gallons and pints and quarts. We use the metric system. A rough correspondence, you can think of there as being a roughly 4 liters per gallon. Now, that's really not true. A liter is a little bit bigger than a quart. There are 4 quarts per gallon. I think it's actually 3.785 liters per gallon. But for a rough estimate, you can think of 10 gallons, roughly 40 liters. That's about how much fluid there is in a typical 150-pound person. Now, about 2/3 of that, 65%, is intracellular fluid. That's inside of the cells. 35%, or roughly 1/3, is extracellular fluid that is outside of the cells. Now, there are several different kinds of extracellular fluid. Interstitial fluid, I mentioned before, is the fluid in between cells. That makes up 25% of the total fluid in your body. 1/4 of all your fluid is interstitial fluid. 8% is blood plasma and lymph. As we'll see, lymph and blood plasma, by the way, is the watery part of the blood. Lymph comes from blood plasma, and ultimately all lymph drains back into the blood and becomes blood plasma once again. So those are essentially the same fluid. 8% of your total fluid. And then 2% is the leftover. We call it transcellular fluid. That's things like cerebrospinal fluid, aqueous and vitreous humor, remember from your eye, bile, synovial fluid, remember in synovial joints, urine, tears, other stuff as well, okay? So these numbers can vary by sex, age, overall size, percent body fat. I mean, obviously, they're not exactly the same for everybody. I mean, I say that you have, roughly 40 liters of fluid. Kevin Durant, 6'10" or whatever, 270 pounds, he has a lot more than 40 liters. So, they're going to vary according to your overall size and your physical condition as well. So, who do you think will have the greater percentage of water, a lean person or an obese person? All right. I said up above, you have between 50 and 60% of you is fluid. So who is going to have more, a lean or an obese person? We do this a lot in Bio 2. We have a lot of critical thinking questions, and there will be critical thinking questions on a lot of your quizzes and exams. I haven't told you the answer to this, but I expect you should be able to figure it out. We'll have a lot of those kinds of questions this semester. So think about it. What do you know? There's an old saying. What do you know about oil and water? Oil and water don't mix. What's the difference between oil and fat? Basically just the melting point. Fat that's solid at room temperature we call fat. Lipids that are solid at room temperature we call fat. Lipids that are liquid at room temperature we call oils. So oil and water don't mix, neither do fat and water. So generally speaking, lean people have a higher percentage of water. So that 50 to 60%, 60% are going to be like Olympic athletes. 50% would be obese. Who has a greater percentage of water, do you think, men or women? You should be able to figure this out. As you may know, women have a higher percentage of body fat on average. And why? Because women are the ones that have to carry around those little parasites inside of them. So you need to feed the parasite. It's going to live off some of that. And women need more stored energy. Remember, that's what lipids are. They're stored energy. So women tend to have a smaller percentage of water. Men tend to be leaner. They have a higher percentage of water. Who do you think has a greater percentage of water, old people or young people? Well, as you get older, you tend to lose muscle mass, and you tend to gain adipose. So that means older people will have a smaller percentage of their body weight due to water, okay? These are figure-outable, all right? So they're lean, and men, and young, all right? Men, more water. Young people, more water. Lean people, more water. There's a nice little graphic. I'm not really going to go over it. A good study slide shows also the ions that we're going to be talking about coming up, all right? So check that over. Spend 5 or 10 minutes looking that over. It'll help it sink in. It'll help you remember it. What do you think, true or false? ISF makes up about 25% of your total body fluid. I expect you to know all these numbers, all right? They'll show up on quizzes. That's true. Interstitial fluid is about 1/4 of your total body fluid, okay? So take a look here. Here you see a blood vessel with a red blood cell in it. There you see cells of the body, and there is a lymphatic vessel as well. The blood vessel we're seeing straight on. The lymphatic vessel we're seeing from the side. So look at all the different fluids there. What do we see inside of the cells? We see ICF. That's the salt water inside of the cells. You're basically filled with salt water. We came from the ocean originally, so we're full of salt water. So the cells of your body contain intracellular fluid. Then look at the spaces between the cells. That's ISF. Remember, ISF is interstitial fluid. That's fluid in the spaces. Blood is ECF, but notice red blood cells inside of the blood, inside of a red blood cell would be ICF, okay? Get used to your fluids, all right? And notice that water and solutes are constantly moving around. So ISF is the salt water that surrounds the cells. Blood, lymph, ISF, ICF exchange fluid and solutes constantly. So look, see the arrows going in and out of the blood, arrows going in and out of the cells, arrows going into the lymph. Lymph picks up ISF, all right? It doesn't normally leak it out. But fluids and solutes are moving around like crazy inside of your body. That's always happening. That's what's keeping you alive. And here, once again, we see cells and blood vessels bathe in ISF. They're completely surrounded by it. ISF fills all the spaces between things inside of your body, all right? Constant exchange of water and solutes between ICF, ISF, blood, lymph, and other fluids keeps us in homeostatic balance, all right? That's what has to happen. We have to move things around in order to keep things relatively constant inside of our body. I mean, think about it. We eat things, we urinate, we exercise. All those are going to change proportions of fluids and solutes, so we constantly have to keep readjusting. And here you see, look, you drink things, goes into your digestive tract. From there, fluid goes into your blood. It leaks out of your blood, becomes ISF. It's picked up by cells. It can become ICF. Likewise, cells can give off fluid that becomes ISF. ISF is picked up by the lymphatic system and ultimately returned to the blood again. So look at how all the fluids, and of course when the fluids are moving around, the solutes are moving around with them, okay? So the movement of fluid and solutes between compartments allows the cells of the body to obtain nutrients and eliminate wastes, which is what cells have to do. Okay, so remember all the way back from Bio 156, cells of your body are surrounded by cell membranes. The plasma membrane, they call it, the phospholipid bilayer. Why is it called a phospholipid bilayer? Because it's two layers of phospholipids. Phospholipids are lipids. They're fats, okay? Now, notice they have two sides. You see phospholipids in the upper right-hand corner. By the way, looking on the left side there, you see a cell membrane. Inside the cell, we would have intracellular fluid. Outside of the cell, we have interstitial fluid, right? And then look at the phospholipids in the upper right. So phospholipids have a hydrophilic head and a hydrophobic tail. Hydrophilic, remember, means that it's water soluble. It likes water. So it faces out to the fluid. So notice on the left-hand side, see the cell membrane there, all those yellow phospholipids. Notice the heads are in contact with the ISF, and the heads are also in contact with the ICF. And then it's the tails that come together in the middle. The hydrophobic tails face each other, forming a barrier. Now that's a barrier that prevents things from getting in or out of the cell. Now remember, back from Bio 156, some things can diffuse across membranes. Diffusion allows things to basically wiggle across. Other things cannot diffuse across, so how do they have to get across? Through channels and pumps. And there you see a channel. So a channel will allow solutes to move back and forth between the inside and the outside if they're unable to simply diffuse through. So some things can diffuse across, other things need channels or pumps in order to get across, all right? Structure of the phospholipid bilayer was, by the way, was not determined until after I was born. They used to think that cell membranes were what they called the protein sandwich. So I know a lot of this stuff you're thinking, well, this is old-time stuff. No, it's actually kind of new stuff. I mean, I know I'm old, but still in the history of science, 1950s was just an eye blink ago. Okay, the phospholipid bilayer. So cholesterol stabilizes the membrane. There in the upper right, you can see little molecules of cholesterol. If you watch TV, you might think that cholesterol is bad. Cholesterol is good. In fact, it's essential to life. You can't live without cholesterol. Most of the cholesterol in your body does not come from your diet. You make it in your liver, all right? So, integral and peripheral proteins form channels, transporters, pumps, and receptors. So on the left-hand side, see, as I was mentioning a moment ago, some solutes can diffuse across the membrane. Others need help in the form of channels, transporters, pumps, and then receptors are things that solutes can bind to in order to cause the opening and closing of channels, for example. So what kinds of things can diffuse across? Well, water. And you're thinking, wait, water? How can it get across the phospholipid bilayer if the phospholipid bilayer is hydrophobic? Well, water is a tiny, tiny molecule. It's H2O, all right, just two little hydrogens and one oxygen. So water, even though water is obviously hydrophilic, it's so small that it can wiggle across. Gases can go right across. Small nonpolar particles. Nonpolar means non-charged. Right? Charged molecules are going to have a tough time. But as long as molecules are small and they don't have a charge, they may be able to wiggle across. And all hydrophobic solutes. Hydrophobic love the phospholipid bilayer because the inside is hydrophobic. So they pass right through. So we're talking about fatty acids, in other words, fats like from your diet or that you make, steroid hormones, fat-soluble vitamins will all diffuse across easily. And you need to know your fat-soluble vitamins. They're A, D, E, and K. I'll keep trying to remind you of that. Steroid hormones, including cortisol, cortisone, aldosterone, estrogen, progesterone, and testosterone, those go easily across, and that's why steroid hormones are so powerful. They have such powerful effects on the body because they can enter right into the cells of your body. Other hormones, we'll see like peptide hormones, they can't get across. They have to bind to external receptors. That's why steroid hormones are so powerful. They can diffuse right into your cells. Fat-soluble vitamins are A, D, E, and K. Now then, large molecules and charged particles and hydrophilic solutes, those can't diffuse through. They need help. They need channels or transporters. So big giant molecules, any molecule that's charged like an ion, and molecules that are water soluble, they need help. They cannot diffuse across. Okay? Here's a nice slide that shows a summary of all these things. Okay? So if I were you, I'd spend some time going over this slide. It shows a lot of common solutes that we're going to be dealing with regularly. And in case you can't figure it out, it gives you the answer right here. So you can always check yourself if you're not sure, okay? So it's time to play Will It Diffuse Across? Alrighty. So you play the home version of the game, okay? See if you can get all these right. What do you say? Carbon dioxide, will it diffuse across? What's the answer? Yes. Now why? That's the important thing. I mean, anybody can flip a coin and get the right answer half the time, but why? Because it's a gas. Gases easily diffuse across. What about vitamin B? The answer is no. Vitamin B is one of the water-soluble vitamins. It cannot cross, okay? Glucose. What do you think? Glucose? No. Glucose is a big molecule, and it's water-soluble. Now, do the cells of your body need glucose? You bet they do. They can't live without it. Remember, every cell of your body has to be making ATP in order to stay alive. And what does it need to make ATP? Oxygen and glucose. So the oxygen gets right in. Glucose can't. So therefore, since we have to have glucose, it must get across. If it's not able to diffuse, what do you think? How does it get across? Yeah, transporters. We're going to be talking about glucose transporters this semester. They're a big deal. What do you think? Fatty acids, like from your diet, or ones that you make? Yes, because they're lipid soluble, all right? They're fat soluble, therefore they diffuse right across that phospholipid bilayer, which is a fat soluble membrane. Water? Yeah. Again, water is hydrophilic, but it's tiny. Water's a tiny, tiny molecule, so it can diffuse right across. What do you think? Alcohol? Oh yeah, alcohol gets an easy pass, all right? That's why you guys go out on the weekend and drink alcohol and call ex-girlfriends and boyfriends at 3 o'clock in the morning. Alcohol goes right into the brain. So yeah, alcohol is small, And it's not exactly hydrophobic, but it has kind of both properties, but it's small and it's able to diffuse across. What about urea? Urea is one of the main waste products in the blood. You need to know that. We're going to be talking a lot about urea. Urea can make it across. Urea is about the biggest molecule that can diffuse across. And in fact, you'll see some of the diagrams show that urea kind of struggles to get across. It can get across, but not very easily. So that's about as big as you can be and still make it and be able to diffuse across. What about amino acids? Amino acids, remember, the building blocks of proteins. You've got tons of amino acids in your body. No, they're way too big, and they are water soluble, and they often are charged because amino acids will gain and lose hydrogens at physiological pH, and so they generally are not able to diffuse across phospholipid bilayers. What about steroid hormones? Oh, hell yeah. They are fat soluble. They go right across, okay? And what about the bicarbonate ion? Bicarbonate ion, one of the main ions in your body, is the principal buffer of the extracellular fluid. We're going to be talking a lot about the bicarbonate ion. What do you think? No. Why? Because it's charged. Charged things cannot diffuse across. Okay, boys and girls, that's it for this one. We'll go on to the next one.